Hello everyone and welcome back to my channel. I hope you all are doing good because till the last few days I wasn't feeling very good, so that's why there hasn't been any upload on this channel. After I posted the update that there would be a new video coming out soon, I was down with fever altogether. But today I'm in a much better shape now, and that's why we are going back to learn some CFD through MATLAB. In the last two lectures, we had been talking about the convection diffusion equation. I gave you a glimpse of how you can use the finite volume method, and today we are going to write a MATLAB code for that. So we're not going to dive too much into that. So I talked to you about the upwind scheme and the quick scheme. We won't be dealing about them just now. I'll give you an overview of how to code those lines of theoretical equations that you obtained through the finite volume method into the MATLAB. So without getting any late, let's jump right in. So we were talking about this steady 1D convection diffusion equation where we had one convective term and one diffusion term, as simple as that, right? So because this is a steady state equation, so that's why we don't have any time derivative. So what we did using the finite volume method was we considered a small volume around the point P. Let's say the index of this point P is I, just like we were doing in the finite differencing. Then after considering this control volume, we integrated this governing equation, that is equation number 1, over this control volume, and using that we got this particular grayed out equation that the integration of the convection term from the west phase to the east phase is equal to the integration of the diffusion term again from west phase to the east phase. Once we do that, we get that the east flux minus the west flux, because we have this dx term here, so that gets cancelled out. So today I would be talking about what is called as this central differencing scheme that we were learning, I think 2 lectures ago, that we assumed that the phase flux or the phase variable is the average of the surrounding ones. So using that, we saw that the phi small e was given as the average of phi p plus phi e divided by 2. And similarly, the phi small w was given as the half of phi capital P plus phi capital W. And using that, we arrived at this particular equation, that is AP phi P is AE phi E plus AW phi W. And this is the equation that we are looking forward to code into the MATLAB. But fortunately, we also have what is called as an exact solution for this problem. So I also show you that if you take this particular equation and you impose the boundary condition such that at x equals to 0 you have phi being phi naught, while at x equal to L you have phi equals to phi L, we can write that the exact solution of this particular problem is given in the form of this particular equation here, where we said that the P was a Piclet number, and the physical significance of this Piclet number was that it was the ratio of convection to the diffusion. So the convection here is rho times U, while the diffusion is gamma over L. So that goes into the numerator. And we described certain situations that when the Piclet number is 0 or very close to 0, the system is more or less totally diffusion and the resulting behavior is linear. While if the Piclet number is larger or not equal to 0, we observe certain behaviors. So today we would be trying to see exactly the same. We know what the exact solution is. We know what the central differencing would give us as the form of final equation, and we want to compare these two for many values of Piclet number. So let me go back to the MATLAB and I'll show you the code that can do that, and I'll explain you the lines of code that I'm using here. So again, the first 3 things that I always do is to clear all the variables, close all the figures, and clean the command window so that we start with a nice clean MATLAB setup. The second part is to define the problem statement. So again, like everything else, I'm using 101 points in the mesh, And I'm saying that the total domain length is 1, and that gives me that the grid spacing h, it becomes 1 over 100, or domain length divided by endpoints minus 1. Based on this grid spacing, we can determine, or we can define the x, which is nothing but the x coordinate of each point, because my first point starts with, or starts at x equals to 0, and the final point is x equal to 1 with a spacing of h. So that is why I'm using these columns. So I'll show you what that does. I'll right click and evaluate selection. I'll go back to the MATLAB here, and you can see that I have x equals to 0, 0.1. So it's a 101 pointed vector which contains all the x coordinates or x values of the domain. Now, just for the illustration purpose, what I'm saying is that at x equals to 0, I'm saying that phi equals to phi naught, and I'm giving it an arbitrary value of 10, while for phi equals to phi L, I'm giving it an arbitrary value of 20. So the way in which I do that is, I say that phi at 1 equals to 10. So now that's an important thing to remember from the context of MATLAB, that the first index, it starts from 1. In C, it starts from 0. In some other languages, it could start from something else. But for MATLAB, the first index always starts from 1. So I said that phi at 1 equals to 10 and phi at endpoints equals to 20. And what if I evaluate these two lines, what happens is, you see we have a phi variable, and it happens that the first variable is 10 and everything else would be 0 in between all the way until the last one. It goes back to the last few lectures where I was telling you that if you don't initialize anything, it would simply go back to 0. Or let us say if you are trying to initialize only the last element of a vector or a matrix, everything else before that would be turned out to be 0. So similarly, I'm also assigning a variable called phi new just to store the new values of the phi during the iterative process. So again, the same line of code goes here. And arbitrarily, I'm saying that rho equals to 1, gamma equals to 1, and the domain length is already equals to 1. So using u, I can change what is called as the Piclet number. So you remember the Piclet number is given as rho times u times L divided by gamma. So for now, I'll just choose it to 1 so that my Piclet number is 1. So if I hit Control plus Enter on this particular section, what it does is it evaluates this yellowed out, highlighted, or this section. So once I do that, I can see that the Piclet number is 1 because I haven't put a semicolon right here. If you notice, that's why I can see the output of whatever the Piclet number is. So we know what the exact solution of this particular problem. So I have just written this particular line here. So I'll take you step by step. So we have to go back to what the solution is. So it says that phi equals to phi 0 plus this particular terms multiplied by this whole term. So that's exactly what I've written here. So phi 0 is given as phi 1 in MATLAB. And this is the denominator of the left hand side, that phi L minus phi 0 multiplied by exponential px minus 1. So this is Piclet number, and this is simply exponential of Piclet number minus 1. So you notice that in the numerator, it's Piclet number times x divided by L. Because the domain length L is equal to 1, so it doesn't really matter even if I write the domain length here. So as soon as I do that, so we have the phi exact. So I'll just evaluate the selection. and I'll go back to here. So we have a phi exact, that is a 101 vector. And the next line of code says that figure 1 and then semicolon. So what this command simply does is it opens a new figure, but the another thing it does is it numbers the figure as 1. So I'll show you what I mean. So you see that this is called as a figure 1. Had I written it figure 11, it would do exactly that. It would open a new figure that is numbered as figure 11. This particular numbering is very useful when you are dealing with many variables and you are going to jump back and forth between figures. So let us say you want to plot, let us say we have 3 velocity components, u, v and w, and your code would jump back and forth. So at the first iteration, it would plot u, then it would plot v, then it would plot w, and in the next iteration, it would again do the same thing. So I like to make sure that the figures are numbered so that it's easy for me to assign some sort of index to the figures. So I could have given 11, 12, 13 so that it makes my job easier. If you let MATLAB do it, it would just automatically get the next number and would randomly assign that number to a figure. So just to take a better control of things, you can apply this particular trick that you can number your figure as well. So let us stick with 1 because we don't really have any figures here. So figure 1, I'll open that and I'll also plot the same thing. So a couple of important things actually. So in the plot command, the first variable is called x, which is simply the x location on the x-axis. The second variable is phi exact, that is on the y-axis. So at x equals to 0, phi equals to 10. At x equals to 1, phi equals to 20. The next thing that I'm doing here is I'm putting something in these inverted commas that says R and O. So in MATLAB plots, there are many ways in which you can customize the plot. So for the plot, there could be a line, you can customize that line. In a plot, there could be data points or data markers, and you can customize these markers. So in this particular plot, what I'm trying to do is I'm not plotting the line that goes through those data markers, but I'm just plotting the data markers directly. So the first word here, R, it gives me the color, that is red, and that O, it gives me the shape of the markers. So there are many different shapes of the markers. So for instance, let us close this figure. If I write D, which stands for diamond, so as soon as I hit Control Enter, you can see that the shape of those markers have changed from circular to diamond. You can also go for a different one, which is RP, which gives you a pentagonal star. Or you can go to the MATLAB's website and they have all this list of shapes, list of colors, and many different properties that would go inside the plot. So this is just to give you an idea of what the different capabilities of this wonderful software are. So let us stick with this. So we have plotted the exact solution. Now we want to evaluate the numerical solution. So again, the process more or less remains same. The first two lines are the error is initialized as 1, so that we can go into this while loop, and iterations are 0. So we know that the iterations would be done from, so let me go back to this picture here. So we know that the index of P is I, while the neighbors is I plus 1 and I minus 1. And since the iterations are done only for the last, are not done for the last or the boundary points, we only do the iterative procedure for the interior points. And if you don't remember this, I recommend that you go back to some of the lectures and try to understand why we are exactly doing this. So for all the interior points, we are saying that AE, so now we have to go back to here. So we want to code this particular equation which says that the phi P, or the new value of phi P, is given as AE phi E plus AW phi W divided by AP. So we know that the phi e is nothing but the variable phi at the point e, which is I plus 1. Phi w is phi at I minus 1, whereas phi p is phi at I comma. So we need to tell MATLAB what are the value of these AE, AW and AB. So we know that from the theoretical parts that AE is given as GE minus FE by 2. And the D is gamma over delta X or gamma over H in our MATLAB language, whereas Fe is given as rho U. So I have quoted exactly the same. I have said that this is the diffusion term, that is gamma divided by H minus Fe divided by 2. Similarly, I do for AW, which says that the diffusion term plus half times Fw. And similarly, I have written for AP. So you can always go back here to the original equations and cross-check whether what I've written is right or wrong. The next task is then to simply use the discretized version or the finite volume version rather. So the phi nu is given as AE times phi at I plus 1 plus AW times phi at I minus 1 divided by AP. So once the entire for loop is done, we can say that we have performed one iteration, and that is why iterations equals to iterations plus 1. And again, we said that the error is 0 so that we can calculate what the correct value of error is. And we are again taking all the interior points and we are saying that the error equals to error plus, or this is just a way to write the cumulative error of the absolute value of the old phi minus the new phi. So again, if you have been following all these lectures, you would be very familiar with this methodology now, that the error at this particular iteration is the new value minus the old values summed over the entire domain. Nothing new there. And after that, we just assign that the phi is equals to phi new so that we can carry out further computations if required. So I'll run this particular line of the code and I'll show you what happens there. So the solution has converged in around 30,000 iterations. Now, as I was telling you that, so let me skip for a bit. So what we done from the perspective of plotting was, we plot the exact solution using these data markers, and now I want to plot the numerical solution on top of that. So what I have to do is, we have to go back to that original figure that plotted those exact solutions. So to do that, you remember that we had given a number to that figure. So now we can call that number again. So rather than saying MATLAB to find an arbitrary figure, we can tell MATLAB, go and find me figure number 1 or 11 or whatsoever. And then we can use from there to plot this numerical solution on top of that. So I had given it figure 1, and you see that the figure 1 is still open. So as soon as I put this command here, it would open the same figure. It wouldn't open another new figure called as figure 1. It would just open the same figure. And when I say hold on, it means that I want to plot something on top of that. So if I use a plot command, don't erase this existing figure. If you don't use this hold on command and give a next plot command, it would remove this particular figure from here. So again, if I give this new plot command, so I'm plotting the variation of phi, which is my numerical solution, with x. So x on the x-axis, phi on the y-axis. I have put another parameters here, which I'll just show you very shortly. So I'll go here. So you can see that the numerical solution, it fits through the exact solution. And there are a few characteristics here. So this B indicates the color of the line. So by default, MATLAB fits a line through your data points and it does not show your data points. So unless you have specified something about the markers, it would not produce markers. And if you had informed about the markers but nothing about the line, then it would not plot the line like we did for the exact solution. For the exact solution, we provided the information about the markers but nothing about the line. So that's why only the markers. If you want both, you have to give information for both the markers and the line. So in this case, I have provided only the color information. So by default, MATLAB produced a line and then it painted it blue. The next argument here is called as the line width, or in other words, how thick would be your line. So sometimes it's not desirable to have very thin lines in the plot. So by default, MATLAB uses a 0.1 pixel thickness. So you can go further and change it to 1 thickness. So that's what this particular command does. So I am using a comma to separate all this. So the line width is put in the inverted commas. And then I give a comma, proceeded via the value of the line width. So as soon as I do that, we get this blue thicker line on the top of that plot. And finally, another thing that I should be doing here is actually, I'll put the plot side by side here. So as I was telling you, that this is always a good practice to use the labels at the same time you are plotting the figure. So I'll just produce these arbitrary labels. So X label X and Y label phi, so that the people know what these things are. Later I'll show you how you can write the mathematical version of phi or any particular variable using what is called as the LaTeX interpreter. But for now, let us be satisfied with these English version of these labels, just to give some clarity to the person who is looking at these figures as to what they are really about. The final part here is to put a legend, and if you don't know what a legend is, it would become very clear very soon once I click enter. So the legend, because we have these two different data sets in the same figure, and we want to tell the reader or the viewer what these data sets correspond to. So remember, the first one was for the exact solution and the second one was for the numerical solution. So the legend gives the different kind of plots or the different kind of data sets their identity somewhere in the plot. So as soon as I hit this particular command, it says that, so the way in which I have written this is, we have something called as legend, and then in the bracket we have provided two legend entries in the inverted commas again. The first one is called exact solution. The second one is separated by a comma and it's called as a differencing scheme, or you can call as numerical scheme. And again, if you select it and hit F9 or evaluate selection, it would override this particular legend and it would say that the starred one is the exact solution and the blue line corresponds to the numerical scheme. So I hope that today we started off with a MATLAB again, and I gave you some idea on how you can customize your plots much better, and we are trying to get into the finite volume aspect of coding as well. So in the next lecture, I'm not entirely sure when it would be, but because we are now getting very close to the Navier-Stokes equation, we are sort of just one step away from there. Once we go into the 2D convection diffusion problems, then the Navier-Stokes equation is just at the door, because it's almost there. The Navier-Stokes equation is also a convection diffusion equation with a pressure gradient term, which is also very notorious. But we are almost there when we solve the 2D convection diffusion equation. So in the next lecture or so, we'll talk about that. But I hope that this lecture would be useful for you if you are struggling with coding, as I've received many comments regarding that. I'm sorry that I haven't been very up to the date with a lot of comments and their responses. But after this video, hopefully I would be in a much better shape to respond to that. So in case if you have any questions, please feel free to write to them in the comments, and you can expect some response from now on. And if you haven't liked this particular video, please do so and subscribe to the channel so that you can receive further notifications as well. And if you have any friends who are willing to learn MATLAB or CMD, I highly recommend if you can subscribe to if you can share about the channel, I would be very grateful to you. And I'll see you in the next video. Till then, take care. Bye bye.